Hello friends, so hope you are doing well. After a long time due to my busy schedule, I was unable to deliver you lecture, but now I have come up with a lecture again on electromagnetic theory, but keeping in view the fact that it will be very important for you for the combined UPSC Geoscientist examination. The topic I will cover here are mostly there in the UPSC syllabus. So what is the topics? That is for the propagation of electromagnetic wave in ionized gas medium. Already I have delivered a lecture on propagation of EM in conducting medium, and this is similar to that. Many derivations you can follow my previous lecture. In addition to that, there are new topics introduced, that is plasma, ionosphere, occurrence of plasma, and the plasma frequency concept. Along with that, the refractive index and the skin depth concept in the plasma. So let's begin our discussion. So here is this is, please have a glance at the syllabus for electrodynamics. There is a plasma is there, plasma waves are there. In this lecture I am not covering magnetohydrodynamics, later on I will cover. And electromagnetic theory, almost I have covered all some of these Maxwell's equation, differential integral form, displacement current, boundary conditions, wave equations. And here in addition to that I will be discussing about the propagation of waves and the sky wave concept, ionosphere, DEF region. This I am going to concept. This will be very important for your upcoming combined geophysics geoscientist examination in geophysical paper 1, 2, 3. So let's discuss. So you know about the conductivity, current density in ionized gas medium. We know the Maxwell's equation, and we can get the wave equation for linear homogeneous dielectric medium. This is already been derived in my previous Maxwell's equation in conducting medium. You can follow the link for that to get to the equation, my previous lecture. And for using the concept of D is equal to epsilon E and linear isotropic homogeneous medium. And you keep in mind one fact, that the free charge density rho is equal to 0 for the conducting medium, and current density is proportional to the electric field along with the proportionality constant, that is the conductivity sigma. Now when we have sinusoidal electric field, you can find del T is proportional to minus I omega. You can find with derivative, very trivial things, and grad square is minus k square. So you can very easily you can substitute this into the equation, this wave equation. So you have a concept of wave equation and you just replace this, is a very easy way. And you can have the wave form of wave vector. You can see that wave vector in square form, that is imaginary term I is introduced, that is in the conducting medium. This for it is introduced for this term epsilon mu in the first derivative of the electric field. And now you can say that k is does a complex number. So already this is covered in Maxwell's equation in conducting medium, one of my lectures. You can see that in a conducting medium you can find the current density, that is the number density, and NEV proportional to the number density, and you can you have to replace the form of conductivity. So from where can we get conductivity? So we first start with the force term. So you know, in force with electric field and electromagnetic medium, electric force and magnetic force is there. Often the electric force is more powerful than the magnetic force in the conducting medium, and you can assume this term is very greater than the magnetic force. So when you assume this, you can find the force to be as the charge of the electron along with the electric field, and you can write the force in terms of the double derivative in this form. And this is like an right hand side there is a electric I mean the form of electric field is there. From this equation we can get the form of velocity, means first derivative, by integrating this equation. Dr dt means 1 by E by m E0 e to the power minus I omega t divided by I omega, and you get the velocity in this form. When you replace the velocity in this equation, you can get the form of the current density in any ionized conducting medium there with the I term, that is, it is a imaginary, and you can get to the equation famous, this conductivity is proportional to the electric field along with the conductivity proportional term, that you can tell as a conductivity, and the conductivity is the imaginary in a conducting medium, I term is there. So you can say, and this N0 is the electron density of the ionized gas. Often in the examination you may be asked to derive the form of the conductivity from this equation, Maxwell's equation. So you have to start with the Maxwell's equation, you have to replace this linear terms d proportional b and rho is equal to 0. You can reach to the wave equation, and from that wave equation you can derive the wave vector, and from there you can get the conductivity terms in a detailed derivation. So there is a mathematically is there. We will again describe the physical significance of the complex wave vector and the imaginary conductivity. So now the complex wave vector and imaginary conductivity in a conducting medium, say is a plasma. So we will derive the concept of the conducting medium. You can see that wave vector in my previous slide is the imaginary. So we denote it by star. Star denotes the imaginary in a usual concept, because in my previous lecture I have used this term star. So when we replace the term sigma, means conductivity, it appears to be like this equation. So what we can try, if we just write this is omega square, and we write this N0 square by m epsilon 0 omega p square. Let's forget what is this term, we just denote it by omega p square. Now we are denoting omega p as a angular plasma frequency, p denotes the plasma. Now for any medium, refractive index is the velocity of light in the free space divided by the velocity of light in the medium, and you know v can be written as omega by k. From there you can get the wave vector. If you know the, and you know that we denote this term angular plasma frequency as the root mean square of n0 by e square by m epsilon 0, and if we divide by 2 pi it will get to the plasma frequency. And when you, in SI unit, when you put all the terms, you can get Fp is equal to 9 root over of density of the electron. Okay. Now it this plasma frequency is proportional to the number density of the electron. In my next slide I am going to tell the physical significance of the frequency terms. As it is already there in the syllabus, I am covering it as for the preparation of the exam and for your derivation. You can see that when you know the form in that k square, you replace the term k square like it does omega square by c square, and that from there you can derive the dielectric constant, that is the square of the refractive index, and you can, so you can from there you can reach refractive index of any medium can be written as the square root of 1 minus plasma frequency square by frequency of the variable frequency of the wave. Okay, and the same way it can be written as square of the frequency by this term, n square is equal to 1 minus 81 n0 by f square. This is so if you are already provided with the free electron density and the frequency of the wave, you can derive the refractive index of that medium by this equation, and it is used in many ways. I mean very practical cases. I will show you in ionosphere and the lower cutoff frequency of the wave. So there are two cases. First is the frequency of the wave is greater than the plasma frequency. So in that case our term n is equal to real, because it is the less than 1. So in the root that will be real term positive, and the wave propagate without attenuation in the dielectric. Okay, there will be no attenuation physically, but when there is a low frequency term, this I mean the discussion is already, I have given the physical ohmic heat loss in the medium in one of my previous slide, the propagation of electromagnetic wave in a conducting medium, and why the attenuation happens for the wave. But for low frequency case, that is for this k and this n is imaginary and the complex terms. So for imaginary and complex, that I have already discussed, the wave propagate with attenuation, and the dielectric constant, that epsilon r, this term is greater than 1, so this is a negative dielectric constant. So for negative dielectric constant, wave propagate with attenuation, there will be attenuation factor. Okay, this is a very famous equation. So right now, in my previous slide, I was talking and discussing about the plasma frequency. What is up there in the plasma frequency? What is plasma? But I have not discussed about anything about the plasma. And being a plasma physicist myself, I should discuss something about you, or the preliminary introduction about the plasma. So for now, you should realize that what is plasma. There are 3 states: solid state, liquid state, and the gaseous state. And additionally, there is also one state, that is plasma. And next, ionization. Ions will be there, the electrons will be there, and the neutral particle. It is known to be the 4th state of matter: first, second, third, and fourth. But it is a quasi-neutral. Quasi-neutral means as a whole there will be same number of electrons ions is a neutral macroscopically. But when you consider a small volume and there will be edge effects, so their neutrality is violated. So we can say this is like a quasi-neutral medium. Later on I will discuss in detail about the plasma. It is a complex and the non-linear medium, and there are periodic, relaxation, oscillation, intermittent, chaos, various type of non-linear oscillation that you will find, which are a part of the interdisciplinary subject, you can see, and various, and its application is widely spread, means many industrial, household application. You can see cutting, melting, welding, plasma jets, fluorescence, neon light, plasma torch, and most importantly, it is used as a large scale integrated circuits. Its plasma processing technology, surface physics. The electronics industry are using it in a global way, and which is very crucial for this aerospace, automobile, biomedical, toxic waste management studies. So you can see the application of the plasma in our new A and the solid state devices, IC, that are very much popular nowadays. So why the study is important in plasma? So that's why we have to do theoretical study of plasma. So, and if you talk about our nature, outside nature and universe, that is the 99% of the universe is the plasma. You can see lightning, aurora, wind, ionosphere. They are all the examples of plasma. Plasma can be found, the occurrences of the plasma can be found in there. So you may be asked in the exam about the occurrences of the plasma and the applications and the frequencies in your geoscientist examination. Now I will discuss about the electromagnetic wave propagation in plasma. So for plasma, obviously this plasma frequency is greater than omega square. In that case, our refractive index, you can see our refractive index as omega p square by omega square in this form. When you write the refractive index in this form, that root minus 1 is equal to I. So actually your refractive index n would be plus minus of In. That is complex, or already I have discussed the imaginary and the complex. In that case, our skin depth. So you for your enlightening, I should tell about what is the skin depth. Skin depth is the depth, already I have talked about in my previous lecture. Again I am telling, the depth at which the electromagnetic wave is just reduced to 1 by E of its initial amplitude. So skin depth can be written as 1 divided by the wave vector, and you replace the term of k, you can reach to the equation of this. So c by root over omega plasma frequency square minus omega square. So if that we already assume that plasma frequency is very greater than omega, in that case this second term can be neglected, and it is proportional to the 1 by omega p. So more the plasma frequency of plasma, the less will be the skin depth. The skin depth will reduce in the plasma. Okay. It decreases with the frequency and the conductivity of the medium. So more the frequency, more the conductivity, the skin depth will be less. That means the less means the wave will be attenuated very fast. And you can see the pictorial concept. This I have derived for, but for your easiness I have again posted it in my slide. It is a wave, so I think this is a free space. There is no attenuation of the wave for sigma is equal to 0 conductivity. When the wave enters the conducting medium, that amplitude, there's a maximum amplitude, is reduced or damped to 1 by E of its initial amplitude. That means here if the amplitude is E0, capital E0, here the amplitude will be E0 by E, means 1 by E of its amplitude. In that case, we can say this is the, from there to here, the conducting medium. This depth is the skin depth, and we assume when there is a frequency, high frequency wave enters into the medium, again high frequency of that skin depth will reduce more and more. So the damping will be more for more frequency, yes, and the more conductivity. More the conducting medium, more there will be attenuation, and in accordingly the skin depth and wave vector will change. So now I was talking about the plasma frequency again and again. What is the plasma frequency? So to do that, I will discuss you in detail very shortly. So you have a plasma. Plasma means equal positive and negative ions are there, and initially it is at rest. There is no electric field external. By external means some perturbation, we push some small charge separation. So for small charge separation, electron will be displaced by an amount x, but the ions remains fixed. Okay. So excess negative charge on the right hand side, you can see that easily. So the excess and the positive charge on the left hand side. Okay. And we remove the disturbing force instantaneously by a movement. फटाक से हम लोग remove कर लिए. Then what will happen? The positive slab on the left and the negative slab on the right there is a charge separation, so the electric field will be produced at the right. Here the electric field is at the right, here also the electric field will point about the negative charge. So this internal electric field that is produced within the system, that will pull the electrons back, because this negative charge region is produced that pulls the electron back to their original location. Okay, that tries to pull. But for electric field there is an electric force. That electric force accelerates the electron, and electron already gains a kinetic energy. So what they will come, say they will overshoot their electric field, actually pulls the electron back, but the electrons will overshoot their original position. So this movement of the sequence of movement that happens periodically, and which is termed as the fast oscillation of the electrons about the fixed or more massive ion. And that oscillation or that periodic movement of the electron can be termed as the plasma frequency. And the motions that is executed by the electron, that is actually called plasma frequency. Generally within the plasma as a whole, it maintains macroscopic electrical neutrality, but if you that is why it is called quasi-neutral, but at the edges there may be some excess positive or the negative charge, that is violating the neutrality concept. But as a whole, generally the plasma without any external disturbing force, this is as a whole neutral. Okay, so hope I am able to make you understand about the concept of the plasma frequency. You think of pictorially, I mean by closing your eyes. अपना आँख बंद कीजिए और सोचिए कैसा होता है प्लाज्मा में. सब इलेक्ट्रॉन्स और न्यूट्रल्स एकदम फिक्स रहते हैं. नाउ यू जस्ट फटाक से यू जस्ट अप्लाई एक्सटर्नल डिस्टर्बिंग फोर्स. So ions are more massive, they will not respond, electrons will respond, and the displacement of electron will be some amount, that is x. For this there will be internal electric field that will pull the electrons back, and electrons will overshoot their original position, and that happens, that movement is called the plasma frequency. And that concept, that movement of plasma frequency, I have derived by the electromagnetic theory, that is the omega p. I was talking about the plasma frequency concept more and more times, derived it from the electromagnetic waves in plasma, that is called the plasma frequency. Hope you have understood. So now I was talking about imaginary refractive index, dielectric constant. So what is that physical meaning and where can we get this? So already you know that the frequency is greater than omega, that plasma frequency. You can have the decaying form for conducting medium, and it's a standing decaying wave. The wave can only propagate if that wave vector has a real part. For wave vector, that means k is equal to k plus plus I k minus, that for negative, that for I there will be surely attenuation of the wave. For attenuation, the refractive index is imaginary and that dielectric constant is negative, and wave vector like the refractive index is a pure imaginary number. When the electromagnetic waves have lower frequency than the plasma frequency, that means any conducting medium, they are reflected by the plasma boundaries by Snell's law that you can know, or any, suppose the electromagnetic waves is traveling in ionosphere and it has a frequency less than the plasma frequency of the ionosphere. So for that the wave will fall off exponentially and they will be reflected back. But for frequency is greater than omega p, it is a common case that effective dielectric constant is less than unity and the propagation constant is real. So we can propagate without the frequency. When that omega is greater, very greater than omega p, you can know epsilon r with the previous concept tends to 1, dielectric constant, and refractive index also tends to 1. So wave can pass through the plasma like a transparent medium, and it behaves as a non-transparent, non-dispersive medium because the dielectric constant, the refractive index, everything is independent of the frequency. And if there is a no relation between omega versus k, means frequency and the wave number, there is no dispersion of the wave. So this generally, practically, this happens at VHF, means very high frequencies, means depending on this value is given depending on the plasma frequency 30 to 40 megahertz, and that plasma frequency sets a lower cutoff for the frequency of the electromagnetic radiation. Now is next slide we will see how that plasma frequency sets a lower cutoff in an application basis. So that in my previous slides I was talking about the plasma frequency and the pictorial concept of it and the theoretical concept derivation, but where you can just get a feel of the plasma frequency means where it have you can see that is in the ionosphere, and its practical application is the radio wave propagation, the propagation of the radio wave, TV antenna, there you can find it application purpose. So what is ionosphere? This is also a very important concept for our exam. The ionosphere is a layer above the surface from 80 to around 6 to 700 km, and there are 3 layers within the ionosphere. Depending upon the amount of ionization, they are termed as first as D layer from the surface, when you go above E layer and the F layer. And the ionosphere is ionized by the solar radiation, means from X-ray, gamma ray, ultraviolet ray that are coming, that are ionizing the ionosphere, and that radiation ionizes the atoms and molecules within the ionosphere, and we get a space of free electron and ion, that means the plasma. It is creating an environment of plasma in the ionosphere. Okay. When we give any external electric field from a radio signal, the electron in the ionosphere will experience a force. Means subjected to the electric field, they will experience a force, and there will be a motion of the electrons. So that influences within the ionosphere radio wave propagation, satellite communication, very important to distant places on the earth. When you have free electron density of 10 power 12 per meter cube and plasma frequency of 9 megahertz, the radio wave, you can get the estimation of the radio waves with frequency plasma frequency 9 megahertz. So the radio waves of frequency greater than this omega less than this frequency will be reflected, and greater than this will be transparent to the, will be transmitting to the plasma, as by a theoretical concept I was talking about. And you can get the for very high density layer, there is E and F, the density is more, so the electron plasma frequency will be more, and for more plasma frequency there will be the cutoff will be more, so waves will be reflected from the ionosphere, that will initiate the radio wave propagation more in the E and F layer. The reflection allows the transmission from one point of the earth to the another point. By multiple, this term you can notice ionospheric reflection will be there between any 2 points, that must be very distant point. And when you actually need to communicate with satellites in lower earth orbit, means communication satellite 2000 km, the frequencies above that plasma frequency must be used for the wave to propagate within the ionosphere. because if the frequency is less than that fp, the waves will be reflected back simply. So there will be multiple ionospheric reflection here. This is the two places of the earth communication. This point may be very far enough from this side of the earth to there. There will be from waves go here, reflect here, then again reflect back, then again. So it will be a multiple ionospheric reflection from the wave, from the surface of the earth. Depending upon the frequency, this phenomena is happening. The very important radio wave and satellite communication. Now this you have to guess from where this term comes. You can get from Snell's law, n1 sin theta 1, n2 sin theta 2. For refractive index is 1, so again you can get into second region sin theta, and I is the angle of incidence. For theta second one angle of incidence 90 degree, you can get this epsilon r means n square is equal to sin square theta I, and from my previous slides I have written these terms as that n square 1 minus. So there will be a cutoff for electron density for any region, and which depends upon the dielectric constant of the medium as well as with the frequency. Very important term. So this is the minimum electron density it is required to achieve that total internal reflection. So 1 theta will be total internal reflection, for theta r will be 90 degree, and this is theta I, and n1 will be 1 and n2 will be n2 square will be epsilon r, and from there for Snell's law we get the term and the cutoff for the electron density. So it is the whole theoretical concept of the means the reflection of the wave and the transmission of the wave from earth surface to from receiver of the from transmitter the earth surface and receiver transmitter to the receiving and transmission part of the ionosphere. This is a multiple radio wave communication. Depending on the equation, most of the radio wave signals are communication are carried. Now let me show you one pictorial concept very easily. There is a sun, there is extreme ultraviolet and radiations are coming from the ionosphere, solar X-rays. There is a 3 region of the ionosphere. You should you should read D, E, F regions. What are the densities, electron densities, and how these regions are formed. That D region, that ionization, that F region will be vanish at the night. The visible lights that are solar X-rays are coming and ionizing the ionosphere, forming, and there is a broadcasting and communication satellite. The frequency of the wave will be more above 2000 kilometer communication that I have already discussed. There will be navigation satellite, GPS. To communicate we need to have a cutoff frequency. This cutoff frequency are different from the radio wave propagation, and there is also HF communication, broadcast, TV, FM radio communication in the wave, and there is also aeroplane that is in the layer of stratosphere, I think you know. So this is the whole space wave concept of frequency and the wave, and there are land, surface, and the navigations are being carried out. The satellite operation is there, receiver, transmitter, satellite, everything is pictorially shown here, and this is the HF communication and the broadcasting. So I hope with the theory you can match this with the concept and know about the practical and concept of the plasma and relate it with the theoretical terms. So if you are reading the theoretical concept, you should know its practical concept. That will help you in the practical purpose, and the visualization part is more important for you for any exam. That will help you obviously. So this is my channel. I hope you have enjoyed my lecture. For any difficulty, please let me know. I will be there with you. And this is my channel name, Physics Geophysics Learning. सबको मेरी तरफ से हैप्पी दिवाली टू यू. Stay your days and best of luck for exam. And in my previous lecture, I was also coming to how to cover the different aspects of the syllabus, mainly electrodynamic theory and the physical part, that is having a close relation with the geophysical part. Thank you very much.